Hi, we're going to talk a little bit about electric flux and Gauss's law. And so here's a few definitions you need to know. Flux is the amount of something passing through an area or volume. So this is going to be like a flow of some sort. And what we're mostly interested in is electric flux, which is going to be a measure of the electric field passing through an area. And you'll see the symbol for this is a capital phi. Part of understanding what's going on is we're going to be talking about opened and closed surfaces, and these are just geometries. Open surface is something, could be like a sheet, could be wavy, could be flat, could be a circle or a square, could be any, or just a plane, something that's convenient or something that's completely undefined, but it doesn't wrap around on itself and enclose a volume. The other item is the closed surface, and that's any shape that encloses a volume. It can be a random shape. We're going to mostly deal with cylinders and spheres, maybe some squares, things that are nice and regular. And then we're going to introduce the idea of an area vector. You guys have talked about I hat, j hats, and k hats as being unit vectors. We're going to have an additional one that is called an area vector, and the unit vector for that is a normal vector. So the area vector just represents the magnitude of the area, and it's perpendicular to the actual piece of area that you're talking about. And you'll see that it's an n hat is what that is. So it's like the normal vector. And so, like I said, flux is the amount of something that passes through an area or volume. And here is the equation that defines flux. So you've got flux is the electric field with the dot product with the area vector. And that works out to be EA cosine theta, where theta is the angle between those two, the field and the perpendicular vector to the perpendicular vector to the area we're talking about. Okay, let's talk about the idea of flux. And we'll start with flux being a flow, and in this case it's the flow of electric field through a surface. And the nice thing about this is we can kind of define the surface. Sometimes in problems you'll be given a specific surface, but later on you're going to find that being able to define the field, define the surface correctly for the problems will help you solve them in a nice straightforward fashion. But first we have to talk about where this idea comes from and where it's going. So you have the flux, which is this phi, and it's equal to the dot product of the electric field and an area vector. And the area vector is the idea that there is a vector that represents the magnitude of an area of an object, and the vector is actually perpendicular to whatever that area is. And so one of the nice ways that's kind of convenient is you can rewrite the area vector as some sort of a normal vector times the magnitude of the area. And this will be useful moving forward and when we get into Gauss's law. So if you shrink this down to the tiny, tiny piece where we want to know what the flux is through some strange looking surface, you can take all of the little electric fields and the teeny tiny areas, or dA, and sum them all up. And so this is where we get into the calculus of things. So you get phi is equal to, we won't do that one yet. Phi is equal to the integral of the electric field dot product, all the teeny tiny pieces of area. And since we've talked about the whole simplification thing, it's going to be change the dot product to the field and the normal vector times dA. And if this is for a flat surface, and we're going to do for a closed, so this is open surface. And then for a closed surface, you're going to have basically the same equation because you're going to deal with surface area, but you have to integrate it over the whole surface. And you can see where this is going to get complex, especially when you're talking about all the teeny tiny little normal vectors in a closed surface. So imagine a sphere with all those normal vectors poking out of it and having to integrate the surface area of all of those things. So what Gauss's law actually says is that you can go through and calculate this, and these fluxes and it can be either closed or open surface are going to actually become Q over epsilon naught. And we will be deriving that shortly. So for the equation for flux, come on. You're going to have the flux is equal to the integral of the electric field, dot product with the normal field, and then the dA, which can be written as Q over epsilon naught, where Q is the charge, and this is going to be a net charge because superposition is still valid. Epsilon naught is the constant permittivity of free space, 8.9 times 10 to the negative 12 Coulomb squared, Newton squared, meters squared. All right, so now that we've talked about flux a little bit, we're going to introduce Gauss's law. And Gauss's law says the flux of an electric field through any closed surface is equal to the charge inside divided by the permittivity of free space. And then show you a little derivation for Gauss's law. And we'll have some examples tacked on at the end that will help you calculate flux given that information. It's a very handy equation. Okay, let's talk about where Gauss's law comes from and kind of show you why it works the way it does. So imagine we have a charge Q, and we have a sphere around it, nice hollow sphere. And if you imagine this sphere, it has a radius r. You can see that the electric field coming out of the charge is going to go out from the sphere perpendicularly, and also those little normal vectors that we're going to use to help represent the area vector are going to be in the same direction everywhere on the sphere. And so we can write the electric field of that point as 1 over 4 pi epsilon naught Q over r squared in the direction of the radius. And if we're asking about what is the flux, it's going to be the integral over the surface of the sphere of the field dot product with that normal vector dA. And so let's look at plugging things in. So the field is 1 over 4 pi epsilon naught Q over r squared. We have r hat. And then n, the normal vector, is also r hat. So we've got two r hats there, dA. So 1 over 4 pi epsilon naught q over r squared is all constant, so that comes out. And we're left with the dot product of r hats dA. This dot product goes to 1. And we have 1 over 4 pi epsilon naught q over r squared times the integral of dA, which is 4 pi r squared. Remember that the area of a sphere is 4/3 pi r cubed. So when you integrate that, you get 4 pi r squared. And so we can do a bunch of canceling, and you get the flux is q over epsilon naught. Pretty cool, huh? Okay, so I have some examples of solving for flux for you, both with calculus and with Gauss's law. And we're going to start off with finding the flux through a square. And in this case, the field is at a 60-degree angle to the plane. So we are going to use the idea that flux is going to be EA cosine theta. So let's see. If our field is 2 times 10 to the 4th newtons per coulomb. Okay, so now here's kind of the fun part of Gauss's law. So here we have this random weird looking surface, and there's a 3 microcoulomb charge inside the surface, and we have 2 other charges outside the surface. And so if we're going to talk about what is the charge inside the surface, it's just going to be the value of Q1 divided by epsilon naught. But if we take this and we change our surface and pick something different, so let's have a surface that encloses Q1 and Q2. So now we have Q1 and Q2. So you're going to have the sum of Q1 and Q2 over epsilon naught. So that is going to be minus 1 microcoulomb over epsilon naught. And then if we enclose all the we get the flux is going to be Q1, Q2, Q3 over epsilon naught. And so that is 3 minus 4 minus 1 plus 2 is 1 microcoulomb over epsilon naught. So it's all depends on what's inside your surface. And so our last one is kind of similar with the geometry. What's the flux from a charge enclosed in a cube? So we start off with that same equation. Flux is Q inside over epsilon naught. So whatever that charge is divided by epsilon naught is for the whole cube. And then if you just wanted to know what the flux is through one side, you would just take 1/6 of it, because that's 1/6 of the surface area. So you see that this is very geometry dependent, and that'll be very handy moving forward.